Welcome everyone to this first live session of the 8th International Electronic Conference on Sensors and Application. My name is Anna and I will be your host for today. This conference is hosted online from 1 to 15 of November 2021 and is being organized by MDPI and the journal Sensors. During this time, the conference presentations will be available for discussion on the conference website, and all the accepted proceeding papers will also be available in the journal Engineering Proceedings. Furthermore, the journal Sensors will publish a special issue of the conference proceeding papers. I would like to thank the conference chairs, Dr. Stefano Mariani, Dr. Alberto Vallan, Dr. Stefan Bosse, and Dr. Francisco Falcone, along with the conference committee for making this conference possible, and to all of our speakers and the attendees, of course. I would like to remind everyone that this live session is being recorded and that the recording will be made available as soon as possible on the conference webpage. And that today's session is also being live streamed on MDPI's YouTube channel. So hello to those of you watching us through there. Today we will have 6 selected presentations of 15 minutes each. The presentation will be followed by a question time moderated by the chair. So if you have any questions to our speakers, please feel free to post them in the Q&A box that you will find next to the chat. And please add the name of the speaker you are addressing your question to. Finally, the last thing for me to do is presenting today's session chair, Professor Stefan Bosse, who is an interim professor at the University of Koblenz-Landau and a lecturer at the Department of Computer Sciences from the University of Bremen in Germany. Thank you, Stefan, for chairing the session and handing over the microphone to you. Everyone, enjoy.
Yeah, thank you, Anna, for the kind introduction. And yeah, most of them is already said. What's the goal and the objectives here of this session? The first session today, live session. My name is Stefan Bosse. I'm my research is addressing sensor networks, sensor data science, including artificial intelligence, not only limited to machine learning. That's obviously the well-known part of artificial intelligence. And so, originally I'm a physicist, so I have a real background in the physics and the technology of sensors. And this is an interesting part here, especially of this session and of other sessions of this conference, that we have a broad range of different disciplines that are here coming together. Here you see the different sessions we have in this conference, and this is a very broad range from structural health monitoring and sensor networks, illuminating computer science and sensors, and so on, energy management, and so on. Then we have some application areas. We have wearable sensors, smart cities, optical sensors, sensing and imaging that will be addressed today here in this session, positioning and navigation, sensing for robotics and automation, and finally, one of my special sessions, ultrasonic monitoring of fiber metal laminates. You see, we have a very broad range of different topics, but all under the hood of sensors and sensing. And of course, one important sensor is here explicitly missing. Maybe it's here part of smart city, that is humans, or that are humans, that are you and I. We are sensors, and we can provide sensor information by wearable sensors in smart city context, maybe with some optical sensors and so on. And some traces of our life maybe will be found by satellite images from the Earth and so on. So we are sensors too. And to have today sensing of human thoughts and of intellectual properties in your mind, we have here some interesting talks today, and the first talk that will start will illuminate the use of ultrasounds and is held by Aleksandra Kalinowska. So I will finish my introduction some minutes before the original starting point, but just left some time for preparation. So I ask Aleksandra if you are ready for presentation.
Yes, I'm ready. Hello.
That's great. Okay. So here in the chat, you have already said you have the possibility, or the participants have the possibility to ask question in the question and answer dialogue here, more or less in the center of the bottom bar, and right side you have the chat, and so you can interact with other participants via the chat, and you can discuss some things. And probably you can ask questions too here in the chat. I will check both the chat and the question and answer list for new questions, for new recommendations, comments, and so on. And I will read all text comments if they are addressed to the presenting authors. Okay, now we are on time, and if you're ready, Aleksandra, then I will give a short introduction to your talk. It's the title, The Use of Ultrasound in the Preparation of Chemosensory Microstructures. So we are actually here in the micro level, and on the material level, on the molecule level. And you are coming from the Warsaw University of Technology. And I think you will give an interesting talk about the material inside, the molecular level, the chemistry level, and we will see some other presentations here coming on the large scale. Here now we are on the micro scale level.
So thank you for the introduction. As already mentioned, my name is Aleksandra Kalinowska, and I am PhD student at the Warsaw University of Technology in Poland. The dissertation topic is to use nano or micro materials, such as nano or microspheres, to create sensor arrays for differential recognition. Their task is to identify and quantify selected analytes with a similar structure. Since I am at the beginning of my science path, and the first stages of my research are based on optimizing methods for the production of such chemosensory systems. And so in this work, I would like to present how the use of ultrasound influenced the structure I produced. Ion selective electrodes have been recognized as powerful analytical tools for many years. And we all know the bulk optot well, which in their composition contain chromoionophore, ionophore plasticizer, ion exchanger, and polyvinyl chloride. One of the research lines dedicated to analytical chemistry is developing new sensors and improving existing sensors to meet the growing demand, including the type of analyte, its concentrations, the complexity and selectivity of the sensor sample necessity to miniaturize, and ease of use. The systems that I manufacture contain the same components as in bulk optots, except for polyvinyl chloride. Its place is replaced by a surfactant, and the role of which I will describe in a moment. I will now present the primary materials that form the basis of the systems being created in this work. Sensors are made up of several types of compounds. Of course, the combination of materials depends on the target ions tested and may vary from case to case. First, it's a surfactant, and surfactants prevent particles from coagulating. With their help, it's also possible to obtain particles of an appropriate size. There are two types of surfactants, ionic and non-ionic. Ionic surfactants can interfere with the detection process. Therefore, non-ionic surfactants are more often used. Another, chromoionophore. The chromoionophore acts as an optically active ingredient with its pH sensitive to pH indicator. Typically, this compound is a Nile blue derivative, phenylphthalein derivative, and fluorethane derivative, and etc. It's characterized by a different absorption and emission spectrum from the protonate and deprotonate forms. The presence of the ionophore is to ensure the selectivity of a given system. Such an ionophore usually shows no change in the absorption and emission spectra. Another component is an ion exchanger, which has the ability to exchange its own ion with foreign ions that are in the solution. It should also be highly lipophilic to prevent the leaching of its molecules from the receptor layer. The most commonly used ion exchangers are organic compounds based on tetraphenyloborates or lipophilic ammonium salts. And the last ingredient is a plasticizer, and it's a solvent for all chemosensory active components. Okay, so Eric Bakker is credited with reviving the field of ion selective electrodes and other types of chemical sensors, and the concept of membranes using selective ionophores. He has published over 280 articles that have been cited above 13,000 times worldwide. Now I will present you with one of the sample nanospheres found in Bakker's work. Professor Eric Bakker and his colleagues are trying to create ultra-small ion-selective nanospheres using simple methods. The researcher used various techniques to produce different types of polymer, nano or microspheres, and among other things, developed system without a rigid polymer scaffold, that is the so-called micelles that are stabilized with a surfactant or emulsifier. The sodium ion was used here as the analyte ion. So as you can see, it contains the sodium ionophore, which will provide us with selectivity for this element. The process of preparing such a layout is as follows, and the ingredients in the table are weighted and dissolved in the organic solvent, which is tetrahydrofuran. The resulting cocktail was then poured into the ionized water, keeping the tube on a shaker. The next step was to remove the solvent by blowing in with compressed air. Dynamic light scattering shows that these particles have monodisperse size distribution with an average diameter of about 30 nanometer, suggesting that the nanoparticles are among the smallest ionophore-based nanosensors reported to date. The nanosphere system was characterized by absorbance and fluorescence spectroscopy, and as shown in the figure, several Hofmeister selectivities were observed without adding the ionophore. After the addition of sodium ionophore, the nanoparticles became highly selective for sodium. For the first time, ultrasound was used to create an emulsion in the 1920s by Wood and Loomis. Since then, many scientists have used ultrasound in their research. The main goal of the experiment was to check how the obtained systems would be affected by the addition of ultrasound. Their influence on the chemosensory properties was investigated and their size was checked. Many techniques are used to obtain the most miniature possible systems, including interference in the composition, surfactants, or mechanical interference, for example, quicking mixing, increased pressure, or ultrasound. In my case, after removing the organic solvent, the assembled systems were subject to ultrasound at various times, intervals, and examined for chemosensory properties in absorbance and fluorescence mood. The systems I made were designed to be sensitive to lipophilic ions and cations. And so in their composition, they contain the appropriate chromoionophore, ion exchanger, plasticizer, surfactant, and solvent. We will not find an ionophore in this composition because these systems are not oriented towards one specific ion. The preparation process is the same as in the case of the plan prepared by Professor Bakker, so I will skip this stage now. Now I will present the first result for the anion selective system. The ultrasound process was carried out 3 times, 5 minutes, 15 minutes, and 30 minutes. Sodium perchloride prepared in an appropriate buffer was used as the analyte. The signals shown are shown as a change in the degree of protonation of the chromoionophore, which means the normalization of the obtained absorbance or fluorescence intensity towards the signals for fully protonate and unprotonate form of chromoionophore. The graph on the left clearly shows that ultrasound applied for 5 and 30 minutes in the optical chemosensory system caused a slight loss of sensitivity towards the tested ions. At the same time, the linear range did not change and covered a wide range from 10 micromole to 0.1 mole. Sonication lasting 15 minutes significantly deteriorates the sensitivity of the tested system. And the spectrofluorimetric signal on the right gives a similar picture to the data obtained with UV-Vis. And apart from the loss of sensitivity, perchlorides are determined over the entire concentration range. Small error bars testify to the high repeatability of the measurements. The above results refer to the cation selective system. The ultrasonic process was performed in triplicate 5 minutes, 15 minutes, and 30 minutes. Ammonium ion prepared in an appropriate buffer was used as the analyte. In the case of cation selective microspheres, the result obtained for UV-Vis are similar to those for the anion selective system. The use of ultrasound did not contribute to the improvement of the chemosensory properties of the system and could even narrow the obtained linear range. In the case of fluorescence, the opposite effect can be observed, where the sensitivity of the tested system improves significantly with increasing exposure to ultrasound. And here, repeatability is at a satisfactory level. Apart from examining the influence of ultrasound on chemosensory properties, the influence of ultrasound on the size of the obtained spheres was also checked. A confocal microscope was used for this purpose. Based on the observation of the fluorescence intensity of the microspheres, it can be concluded that they differ slightly in their fluorescence intensity. Thus, the use of ultrasound did not significantly affect their size and morphology. However, the fact that K emit a fluorescent signal indicated the inclusion of a chromoionophore in the microstructures. To sum up, for both anion and cation selective microspheres, the size of the spheres was reduced after 30 minutes of ultrasound compared to the remaining times. Generally, the size of the microspheres is in the range of 2 to 5 micrometer. Ultrasound affects the linearity range and sensitivity of both types of microspheres. The effect of ultrasound is visible both in the case of spectrophotometric and spectrofluorimetric measurements. Ultrasound reduced the sensitivity and linearity range for anion selective microspheres, and when used for 15 to 30 minutes for both spectrophotometric and spectrofluorimetric measurements. The reduction of the sensitivity and range of linearity is also visible in the case of cation selective microspheres, but only in the case of spectrophotometric measurements. The use of ultrasound, especially for a long time, significantly increased the sensitivity and linearity range of cation selective microspheres in spectrofluorimetric measurements. And if you have any questions will we not be able to answer, I will be grateful if you send them to the email address provided here. And thank you very much.
Yeah, thank you for this very interesting talk. And now we have a short time for questions. I start with a question concerning the frequency of the ultrasound and how do you measure the ultrasonic intensity, the power or the energy of the ultrasound that was induced in your samples?
Honestly, I don't know how frequency I have. I have to check, but now I don't know. Sorry.
And did you measure the ultrasound intensity, like the power level, the energy, or something like that?
No.
Yeah, thank you for the talk. Now we are coming to the next talk that is held by Humayun Kabir. Okay, I give a short introduction to your talk about the performance analysis of mesh-based enterprise networks. So you're now migrating to another level, to the more or less macro scale level. You present a performance analysis of mesh-based enterprise network using some specific routing protocols. So here we are in the communication domain. And you are coming from the Department of Electronics and Telecommunication Engineering from the Chittagong University of Engineering and Technology in Chittagong in Bangladesh. So now it's your floor.
I'm Mr. Humayun Kabir from Bangladesh. My today's presentation title is Performance Analysis of Mesh-Based Enterprise Network using RAIP, EIGRP, and OSPF routing protocol. My respective co-authors are MD Hassan Kabir, MD Saiful Islam, Muhammad Ghulam Murtaja, and Muhammad Muhyiddin. Here the outline of my today's presentation, which is covered in this presentation. Introduction. Today, the communication based on the network become a integral element in our daily life. Computer network communication is quickly growing in this pandemic situation. We use the video conferencing, video streaming, and sharing file, printing, etc. Are made easier with communication technologies. In this purpose, we use the data transmitted in time with little interruption become a significant achievement in the wireless sensor network. In routing in the wireless communication sensor network played a significant role field to environment orient monitoring, traffic, monitoring, etc. And in WSN, routing protocol is very important task to find a optimal path between the sensor node and base station, or establish the efficient and variable communication between user and base station to another user. That means source to destination. Here I show the figure, which is the routing protocol they implement in our wireless sensor network architecture. In this figure, we show that see that routing algorithm or a routing protocol the work as a bridge between the user application end and the base node end. The problem statement of this research are the design of the routing protocol for the WSN is quite challenges because the multiple characteristics with the different them for the wireless infrastructure network. Several types of the routing challenges are like energy efficiency, complexity, stability, delay, and robustness communication. Above this mentioned the challenges. Here also the some problem statement in this research work. The flow of detected data compulsory from the number source and specific base station. Created data traffic has a significant redundancy of the most of these cases, and time needed to transmit it, the data required as little possible above the cited WSN application. Contribution of this research. In this research, we try to develop in we are determine the how to routing table are determine the optimal path or router of the data packet will be transmitted source to destination. And this research mainly aim to minimize the routing delay problem by determining the optimal path of the data packet to transmit source to destination, to find the delayless routing protocol of the massive mesh-based enterprise wireless network. To create, we also created the two network model in the different software like a Cisco Packet Tracer and GNS3 simulation software. And after getting design our network, we also simulate the various network topology for packet transfer. Observe the performance difference between our proposed our using routing algorithm like OSPF, EIGRP, and RIP. Here, the concept of the mesh-based enterprise sensor network, we see that the core network design of the mesh-based enterprise network. In this network, if router or wireless sensor node connected each other, when one path is the fail in this router, another path is used for to communicate each one to another router. Here the scenario of our analysis, the mesh-based enterprise simulation model, where we also 10 router to our network design, and each router has we use the one user to communicate communicate each to another one to another user, which is we also denoted PC1 to PC10. And the router also we define this area basis router, area 1 to area 10. And in feature we also increment the user by using the switch and another networking device. Here the IP configuration table of our routing port and the client. Each router, here we see that the previous slide, each router connected to every router. Here we also I also mentioned this. Use the 10 router. Each 10 router connected to each other like a star network. At this for this moment, the all routing port are need to configure for this connection purpose. Here the testing scenario. First of this, we setting our sensor node or like a router, then sending a packet. Here we sending packet. We use to data voice and HTTP file. Then full mesh test the destination full mesh test code, which is a test router, which is means the source to destination target, termination of the test, setup time, and the result. Here we show that the here the T convention procedure. First step, the receiver and transmission network information. Second, to find the best path to location and adding to the routing database. And finally, proceed to identifying and responding, notifying the network changes. Here the first data transmitting by using the rerouting protocol. In this figure, we show that when we using the ping test computer 1, that's been router 1 to router 10, the average or maximum packet delay here is showed is the 0, but here we mentioned the red color box, which is show that they find source to destination the T optimum path to use to get transfer the data. Router 1 to router 10. And figure 7, we show that the another tracer and ping test between the router 1 to router 9 by using the EIGRP routing protocol. This routing protocol also same as result as the previous routing protocol RIP. But when we analyze these two protocol in the difference of like the GNS3, we also get the time difference between this routing protocol. But initially in the Cisco packet tracer, it shows that the round trip times between the source to destination router is 0. Finally, we check our proposed architecture by the OSPF routing protocol. In this OSPF routing protocol, we show that they get the between router 1 to router 10. They also use only one path between router 1 to router 2 because I mentioned in the first, every router connected to each other router by a direct connection. Here the time testing table of our proposed model, mesh-based architecture model for WSN network according to the different routing protocol, right? The EIGRP OSPF. In this table, we show that for full mesh and half mesh, the OSPF take the less time between transmit any kind of traffic like voice, video, and HTTP file. The performance analysis method in this in earlier slide here the in picture, so the sum below, which is the latency and round trip time throughput. The latency is the round trip latency we calculated by this equation, which is equal to round trip time divided by 2, and the round trip time between the delay between source to destination packet traveling time. And throughput is the latency divided by packet size, which is depend on the different kind of method, BPS, MBPS, and GBPS. After calculating the performance analysis meter, we also get our final result, average the average voice packet, the end-to-end latency, HTTP package response time, and the video package end-to-end latency time. And getting this latency result, we also calculate our throughput, which also shown in the figure 10, which is show that the OSPF is get a better throughput any other routing protocol in this test case. And conclusion, in the wireless communication network, identify the optimal path sensor node to destination is the more difficult. The routing protocol have to find the optimal path between the source and destination node, minimize their difficulties. The optimal path of the selection dependent on the several factors, which is also discussed in my paper, research paper. This research, discuss and analyze the different parametric aspect the routing protocol like RIP, EIGRP, OSPF routing protocol analyze to evaluate extend the simulation process using the carefully selected parameter and accurate the feature feature of the routing algorithm and measure the voice, HTTP and video traffic transmit, receiver and receiver, which is mostly uses in this pandemic situation. The routing protocol RIP has shown the most significant uncertainty, whereas OSPF show the demonstrate the lowest latency. Furthermore, OSPF protocol attend the better throughput than any other evaluate the testing scenario. From the above result, we say that the OSPF routing protocol is the more suitable and multi-hop wireless communication network. In this feature, you work this simulation is the more realistic routing protocol also increase the optimization accuracy and hence ensure the efficiency of the routing protocol in terms of wireless communication network network performance. Also, we show that the security purpose issue in this network. Here the references is the yeah. Thank you, time and attention.
Yeah, thank you for this interesting talk. And now we have a short time for questions. Are there questions in the auditorium? In the meantime, I have a short question. How do you address node failures? You address the path finding in sensor networks, but sensor networks are prone to fail due to energy loss, to shortcoming of energy and so on. How do you address node failures?
If any connection between in my slide, here we show that every router connected to each port to another port. When any connection is failed, this link green light is the red right. Indicate this red right, and we get this connection is failed, and the corresponding team take this responsibility to get this connection and make as soon as possible is okay. At this time, a backbone connection between the another part, the routing use the another part. Here we see there's the star network, like a each router connected to the each router like a star. When one path is the fail and another backbone path is the active to transmit a data or the traffic.
Okay. Okay, thank you.
Thank you.
Any more questions? Doesn't seem there are any more questions. Okay, thank you again for your presentation. Now we are coming to the third presentation by Jean-Pierre Ndabakuranye. I hope I have spoken it correctly. Yes. Okay. Yeah, it's now your floor. Please start.
All right. Great talks for the people who came before me. My name is Jean-Pierre from the University of Melbourne, Australia. So my talk will be about the system on chip, SF4 bilirubin measurement in the whole blood. My talk will pretty much be about the system design and all this information. So the results are not a lot, so I will walk you through the design and all the features that we selected. So that's my talk will be more or less about that. First of all, I'll have an introduction, then give you a little bit of the method that I used. This is pretty much the traditional arrangement of a paper, talk about the results and the conclusions. But again, I will be circling around the development of a point of care system for river health assessment. So hopefully you can gain something from my talk. So intro. So yeah, you probably know something called bilirubin, but before I go to bilirubin, there is liver health. Liver disease is a big problem actually. It kills around 1.5 1.5 million deaths per year. And we're talking about around 3 people per minute. So by the end of my talk, around 45 people will be gone due to this problem. So that's how big this problem is. So it's the third cause of death after heart disease and cancer for people who are 45 years or older. And the government of Australia spends around 51 billion per year. So that's a lot of money that this condition takes out of the government's pocket. And you can see it from here. So the way, what happens actually, the liver is has a lot of functions. One of them is to filter blood. You can see if liver is injured, then there will be so the liver cannot do the job of filtering blood. You can see if blood comes, it will pass through a secondary path, so it doesn't. All the toxins and will be dumped in the main circulation. So that's a big problem. You might know bilirubin is that pigment that allows that makes usual kids, babies, grow jaundice. So this jaundice is the yellowing of the skin. It's because bilirubin has become enormous in the blood. And that's pretty much due to the fact that the liver has not been able to filter blood. So how the liver, this bilirubin comes up, it comes from the death of red blood cells. So when these red blood cells die, they will normally go through a number of steps, and they produce what's called unconjugated bilirubin, which has to go through the liver for conjugation, and the liver will be able to excrete it via, the body will be able to excrete it via urine or poop, pretty much. But of course, as just mentioned, the injured liver cannot filter blood well, so that's a big problem. But if you look at the hospital, how people in the hospital do it, when there is a problem with liver, you go to the hospital, they get blood out of the body through the vein or artery. They will take you to the lab, pathology lab, and they will use that information from your blood to get the information about the liver. Needed to say, you realize that this will require people to attend the hospital, and of course, who knows what's going to happen in the middle of the appointments. So a lot of things can happen. And what they're actually looking into your blood, they're looking at the coagulation time, how much time it takes blood to coagulate. And they'll look at some creatinine, there's protein, albumin content. They also look at bilirubin. So there's this guy who demonstrated that actually liver health can be assessed using bilirubin alone. So that's very important. So if you can see this ROS curve, where actually bilirubin alone can be used, it compares a lot with other clinical assessment methods. So that's really good. But the current measurement of bilirubin, apart from this one I've just mentioned, which requires people to go to the hospital, there are some other methods. Usually have optical methods. So this is pretty much spectrophotometry. I believe most people know about spectrophotometry, which is like the standard method for optical measurement. But there is another one for transcutaneous. I will come to this in a minute. But when you look at optical methods and pretty much chemical, they use chemical methods. The problem with these ones is the complexity. So if you go to the hospital, you have like big benchtop instruments, and you understand they require expertise. And not everyone can operate the instrument. And of course, you understand if people have to go to the hospital for blood collection, it will require a certain amount of turnaround times. And of course, we are looking at a very huge instrument, so it's very expensive. Speaking about the transcutaneous, this transcutaneous method, the measurement across the skin, it has been, it's always used on babies or infants. The reason is because their skin is still thin. But when this method was tried on adults, it failed miserably. And that's because the thickness of the skin and the content, we are looking at the melanin and the fat, they will increase as the age develops. So that's a really big problem. And the reason that happens is because you can see, if you look at the absorption coefficient of all blood pigments and plus the melanin of the skin, you can see there will be overlapping. Bilirubin is here, lipid fat is here, hemoglobin is here, that's the blood cell and melanin. So you can see the overlap. So that's why this method has failed on adults. So that was the first motivation. Motivation number two is the technology. If you have been following the market lately, the past decade, you have seen that a lot of industry are going to point of care systems. So that's another motivation. So we have handheld devices. We are looking at, this can be the glucose meter. Everyone, probably most people know about this. The handheld devices can know about the COVID test and transcutaneous testing, as I just mentioned. It can also be a wearable device. It can also be an implant. So these point of care systems have been a huge deal in the market lately. And that's what we are proposing, because of course, if we cannot measure the bilirubin across the skin for adults, and we're looking at cirrhosis, and the cirrhosis is for actual adults. And if you cannot do that, then the only way of doing that, you either go inside the body or you take blood outside. And no one has ever tried that before. So what you can do, you can get a finger prick, take your blood, put it in the device and be able to transmit the information to the GP, and you can get the recommendation about what treatments you can go get from the pharmacy, and all this information can be required. So that's really, really good. And what we proposed, and of course, before I talk about what I propose as solution, this is not trying to sort of replace all the existing practices. It can only supplement it, because the existing method work very, very well, but they have limitations that I've just mentioned. So that can help in avoiding the unnecessary or missed visits. Imagine someone needs to go to the hospital, but they don't have to. So then you can avoid that if you know the information about your blood. And it's probably between the appointments, if there is a surge in bilirubin concentration, then, and you don't have an appointment, then it would be good to know that information, then you don't miss a required liver health assessment. And that gives a better quality of care and can improve the healthcare services. So you understand, if people stop going to hospital because they don't have to, that will improve the healthcare system. And for us, we are looking at using the optical method because of its handiness, and the infection is not a lot. So the methods that we had to use to tackle this problem, of course, so the methods were the principle of dual wavelength. So that's the method that I was using. So we look at two wavelengths and we compare both. So we have the analytic wavelength and the reference wavelength. So that's the main idea of the dual wavelength. So where we have them, we compare both, and we look at the ratio of the analytic wavelength and the reference wavelength. So we can compare, correlate that ratio to the concentration of bilirubin. And we had to choose these features depending on the absorption spectra of bilirubin in the blood. And you can see there is a smaller window here. That's very, very important for us to use this window, which is around 470 nanometer. And of course, you have around green 525, which is green, and that's the reference wavelength. There are several features that we selected. I'm not going to talk about every feature, but these are the features that we selected. Path length is 200 microns. The solvent, we had to use a solvent, the MSO. Also, bilirubin concentration working from 1.2 to 550 milligram per deciliter. You can check the information about why we chose which feature in this paper. So this is how we collected the sample, the blood sample. We did the collection from an laboratory. The reason we chose porcine blood is because it's the closest to human blood, the closest thing to human blood out there. So that's really good that we had to use porcine blood, and we use jugular vein. So they get blood from the jugular vein. Then we use this at different concentrations of bilirubin. All right, so we look at the system, we're describing the system. The system is composed of a system on chip, which is here. They can communicate with the host microcontroller, and we get the data to the computer. And of course, you are doing the measurement across the glass cover here. The sample of blood is here. So we are measuring in transmittance, reflectance mode. You can see how small the chip is. So it's around 7 by 3.5 millimeter. These are other features for the optical module that we used here. So this is the setup that I mentioned. So we have the chip here working in transflectance mode, pretty much. So it goes through the blood sample. There is a reflector on top, comes back, and we can connect the system on the PC, and we get the data how much the concentration there is in blood. I'm talking about the concentration of bilirubin. So the way we do that, we collect sample by sample. I'm talking about the data, ADC data for 1 second. The reason we don't have to take more for more time. If you take more time, bilirubin is degradable on blue light. So you don't want to take long. So just 1 second is enough. And we calculate the other parameters by getting the log of ADC count. Pretty much these are the photocurrents. And we plot R versus bilirubin. So, and you can see very well, they correlate very well with R square greater than 0.9. And the SNR is actually very, very high. A few conclusions and perspective. We did the experiments on dual wavelength using bilirubin estimation on system on chip, as I just mentioned here. This is the system that we used here. And we realized that bilirubin concentration correlates very well with other parameters. Actual other parameters is the term that we invented. We didn't find a better term to use, so we called it other parameter. And R squared is greater than 0.95. And this method can be used in different areas. One would be in industry, can go maybe in agriculture, not just in medical, it can also be used in industry. Yeah, maybe agriculture, medical, and other various areas. In terms of the medical, it can improve the quality of care and improve the health services by reducing the unnecessary and missed clinical visits. And of course, this can be applied medically in hyperbilirubinemia in infants, xanthochromia. This is the intracranial hemorrhage. So, because after the brain bleeding, so we can measure bilirubin and know about this. Liver cirrhosis is also another place where this technology can be used. And when people have the problem of hemolysis, red blood cells breakdown, it can be useful as well. And very critical information when you're measuring bilirubin. The temporal evolution is also critical because you want to know how much bilirubin is increasing per per day. That's very, very important. Thank you very much.
Yeah, thank you, Jean-Pierre, for this very interesting talk, and it's very important and challenging topic. Are there questions in the audience? Okay, in the meantime, I have a question. This is a medical application, right?
Yep.
So at the end, you want to have a medical product, maybe in the future. And in any kind, this is some kind of structural health monitoring of humans. And in structural health monitoring, it's very important to detect sensor failures, or to vice versa, to see it from the opposite view. How can we ensure that the sensor that is the starting point of the information you want to explore and to extract from the human and its health condition, how can you ensure that the sensor is operating correctly, or the sensors? Do you have any algorithms that check the consistency of the sensor or the sensor node you are using?
Thanks, Stefan. Not sure if I got well the question, but I think this is like still on the benchtop. So the next thing would be to validate it using the existing technology. So if you pretty much do the measurement on biofluids, let's say on urine, or let's say on blood, real blood, that can be also possible, or maybe on serum plasma. So if then that can be validated on this, then that would be really that would be cool.
Okay, I think it's
not sure if I had the question very well, but yeah, it's very important. The validation is a very important step.
Okay, thank you for the answer. Any more questions? If not, you have, of course, the possibility to use on site forum I think there is a chat on each for each submission and for each paper, so you can ask questions later. Thank you again, Jean-Pierre, for the.
So I think talk. Anna asked a question, but do I have to answer this now?
Oh, there are questions.
Yeah, Anna asked, I have a question for Jean-Pierre. Are you able to measure blood directly? So this is pretty much the target. So measuring blood directly would be very, very, very good. So we're looking at the amount of blood less than maybe 10 microliters. So just a small finger prick without any pre or post processing.
Okay. Okay, thank you again. And now we have I hope I write, the fourth speaker, Aleksandra Kalashnikov, with the presentation with the title Ultrasonic Oscillating Temperature Sensor for Operation in Air. And it's the second author, okay. And Aleksandra is coming from the Department of Engineering and Mathematics from the Sheffield Hallam University. Now, it's your floor, and please start with the presentation.
Thank you. And my name is Aleksandra Kalashnikov, and I work at Sheffield Hallam University. This is a presentation of our joint research with my PhD student, Ali Luonsi, and it is entitled Ultrasonic Oscillating Temperature Sensor for Operation in Air. So the outline of this presentation is as follows. So first, I will try to introduce you why we think ultrasonic oscillating temperature sensors, or UOTs for short, are useful. Then we will proceed to discuss design and implementation of an airborne UOTs. We will discuss the experimental procedures that we use in order to experimentally evaluate its performance, then results, and finally there will be some summary and conclusions. So what's the motivation for this research? Well, we all know about this greenhouse problem, climate change, all the sort of things. And quite a bit of these emissions are caused by heating our premises where we work and live. And as you can see, there are quite a big proportion of this going for this purpose. So what we can do in order to somehow reduce this or control this? Well, we can just heat only as much as it is necessary, rather than try to keep it all warm and very hot all the time. So in order to do this, we need some temperature sensor, and there is obviously a big market for temperature sensors. It's bigger than, for example, some kinds of microcontrollers, as you can see from the following line. And the only sort of problem, or not problem, but condition here is that in order to measure temperature within the whole room, we need probably several sensors, because temperature can be different in different places in the same room. And what we try to do, what we want to use ultrasound, because it can propagate from one side of the room to another. And during this propagation, the complete temperature will be sensed along the complete pathway of the ultrasound. So we now try to develop airborne UOTs, so UOTs that works in air. And in fact, it's enough to have some sort of simple amplifier and pair of ultrasonic transducers. That amplifier will be an electronic driver. And in fact, for the experiments that I am going to present today, we were, that's all the electronics that was required for this purpose. So it's not overly complicated by any means. So that's how we mounted ultrasonic transducers on the piece of aluminum profile using moons and rings in order to for the transducers to face each other, to be able to move them apart, and just have some sort of controlled experiment. Then we obviously connected all the things together. You can see on the left that's power supply. On the top, this is aluminum profile. We have the electronics assembled on a breadboard here, and also we have frequency meter. So the way the OTS work, oscillating temperature sensor, when they produce some output frequency that is dependent on the temperature between the transducers. And this frequency can be measured, and as it is measured, we can get some idea what's going on in between of this of the transmitter and receiver of ultrasonic waves. Also, you can see near the breadboard we have also variable resistor that is used in order to set up the gain for our driver, for our amplifier, that is essential to compensate for the losses on the propagation of the ultrasound, and also on its transformation from electrical to mechanical energy. So that's the complete ultrasonic oscillating temperature sensor shown on this slide. Right. In order to be able to verify or somehow compare our sensor with conventional sensor, we use this sort of arrangement to measure temperature. So here we have the small PCB that is here, and it contains two sensors, HC20 plus BMP280. They are combinational sensors. They are measuring both the temperature and humidity, but we were interested only in measurement of the temperature. And on the left, you can see a board with Arduino XIAO microcontroller. It has a small display and also SD card, where we were able to record the temperature measurements. And also we used power bank to power this all up without cables from the computer. So here you can see, well, that's basically what you can see behind me. We have some cardboard box where we put all this assembly. Assembly is on the top, so you can see the transducers, ultrasonic transducer. You can also see the sensor here, which is conventional temperature sensor that measures temperature by conventional sensors. We also have electronics, power supply, frequency meter, and also we have hair dryer that will be used to create sudden change in temperature and see how our sensors will respond to it. So enclosure help creating the step change, because obviously it would be difficult to heat up all the room at the same time to see how sensor respond to this change. Right, that's what happened inside. So these sensors, transducer and receiver, were placed inside. The device were taken outside to the driver and to see the frequency. And inside we put this conventional temperature sensor with power bank and with this Arduino Xiao. And yeah, the hair dryer was put inside. Then this was a little bit like closed, and then we switched on this hair dryer remotely for a couple of seconds. The experimental results. So here you can see the results that were obtained by conventional temperature sensor. On the left, we have overall picture where the temperature gone up from about to 20.5 centigrades. We switched on the heater, the hair dryer for 4 times. And you can see that when it was switched on for a short time, the temperature quickly ramped up. First time it was to 25.5 centigrades. Then we let it cool a little bit, right? And interesting thing is that this assembly has 2 sensors, and you can see on the graph on the right that this sensor had different response time, and this showed up as they were when only the switched on the hair dryer. The difference between this the readings of these 2 sensors became quite substantial, like 2 centigrades. But when the heater was switched off, you can see this difference stood at about 1.3 centigrades, so it was quite stable. So yes, that's what happened. As you can see, the both sensors actually responded quite quickly, and then it took substantial time to actually return to the something like the readings that were before, that was the room temperature readings essentially. So what happened to the ultrasound, to the ultrasound results? So here I showed well how we measured the temperature, how we measured the frequency. At the moment we have just started our experiments, so we just put a mobile phone that was filming the readings from the frequency meter, and the frequency meter changed every 1 second. So then we just play frame by frame this recording and took the frequency readings. Here on the right we you can see this frequency reading, and they are shown minus 39 kilohertz, because our transducers worked at about 40 kilohertz, and here 0 means 39 kilohertz. So on the left there are still these readings from the conventional temperature sensors. You can see all the sensors ramp up quite quickly, but when the conventional sensors on the left did very slowly started to return to their pre-step change values, on well, that you can see this all in seconds, right? So after 40 seconds they were still like on 23.5 readings, so 24 on the bottom graph. But at the same time ultrasound returned to, when we switched off the heater, the hair dryer, ultrasound nearly instantly returned to the lower values. So there was no something like memory effect when the conventional sensors were heated for some time. It took them substantial time then to cool down, but ultrasound was free from it, because the air was cooled down quickly, and yeah, we don't have this long tail that was required in order to cool down the conventional sensors to the room temperature values. Right. That's another video when we switched on the heater after short delay. So to see how they will behave. In this case, conventional sensors on the left, they just they didn't return at all to some smaller values, and you see we can see two spikes, but we didn't get anywhere close to the normal temperature in the room. In this, contrary to that, the ultrasound sensor on the right actually showed both spikes, but also it returned very quickly, even when we have the interval between switching on this heater about 40 seconds. So yeah, it was really responsive. It really sense quickly when the temperature was changed suddenly, and we think that's the advantage of this ultrasound sensor. So now we can move on and present a summary and conclusions. So first thing we need to note here is that we described the developed airborne UOTS and compared its response to the temperature step changes, comparing to HC20 and BMP 280 conventional combinational sensors. They measure both temperature and humidity, but we were only interested in temperature. All sensors reported sharp increase in the temperature when the 2 kilowatt heat source was turned on. This hair dryer, it's rated at 2 kilowatts, and we turn it at highest setting. So the UOTS returned to the pre-step readings rather quickly. At the same time, the conventional temperature sensors took substantial time for that. And this qualitatively confirms the faster response time of the former. So we identified ways of improving the design of the setup in order to quantify difference in the sensor's response time. So we need to develop a better frequency counter, and also we need to make sure that we have controlled temperature chamber where we can measure conventional temperature with high degree of accuracy and confidence. Because now we see that conventional temperature sensors actually shoot up like to 25 centigrades quickly, but maybe it was not the peak temperature. Maybe they were just not able to respond to it faster. According to our calculations, when we switch on this 2 kilowatt heater for 1 second, the temperature should have been in this box, should have been increased by about 10 centigrades. So probably conventional sensor didn't actually respond to the full scale. So we will need to build up a temperature chamber where we will compare in the control conditions. We will compare response of our ultrasound temperature sensor to conventional sensors to see. So we can clearly see that response time is shorter. And we also must be able to calibrate to say, well, if the difference is 1 kilohertz, the temperature in the room is 25 centigrades and things like that. So yes, that concludes our presentation, and thank you for your attention.
Yeah, thank you, Aleksandra, for this kind talk and this interesting topic. Other questions? Actually, there's no question. Then I have one question. Do you think you can apply sensor fusion by using multiple sensors, for example, to improve your sensor quality? Do you think about that?
Yes, in fact, in our previous development, when we use ultrasonic oscillating temperature sensor to measure temperature in liquid, right, we found out that our ultrasonic temperature sensor had some sort of hysteresis. So effectively, it was when the temperature went up, it was one frequency measured, but when the temperature went down, at the same temperature, we recorded different frequency. And in order to avoid or to overcome this ambiguity, we use sensor fusion. So we use temperature sensor, ultrasonic temperature sensor with conventional temperature sensor. And yes, we use data fusion in order to combine the responsiveness of the ultrasound temperature sensor, fast response time, with the accuracy that was provided by the conventional sensor. We don't know yet whether it will be required in this case, maybe because, well, the main problem with making a sensor network, for example, for a room, is that you will need quite a bit of wires, or maybe some support for this sensor hanging over the air. So most likely, if we will require this sensor, we will put them near the transducers, conventional temperature sensor, it will not be like a big impact on networking, on cost or whatever. Yeah, we think that it may be required if the airborne UOTs will also feature this hysteresis.
Yeah, thank you for the answer. Here is another question from my colleague, Christoph Polle, very close to my question, but more with a special context. He asked, how sure can you be that the measurements of the ultrasonic sensors are really due to the temperature and not to the airflow, since the values of the ultrasonic sensors quickly return to zero after the hairdryer has been switched off?
That's because it was in the box. That's because it was in the box, and yes, we actually presented another paper. We submitted another paper to the ECSA-8, where we just measured temperature conventionally, and we found out that yes, this is indeed the case. So sometimes there are, we made our measurements, and also we found literature data that even if you put two sensors on the same breadboard, for example, or at very short distance, they can display data like that change that are different by like 2 centigrades. Yes, so that was essential to put this box. That's why we put all this trouble. Well, fortunately, Amazon supplied this box for one of my deliveries, so I didn't need to make it myself or find it somewhere. Yeah, and that was a real issue. That was a real issue. When we only started doing this airborne ultrasonic measurement, we were surprised that they changed quite rapidly or quite unexpectedly. It was not like a same frequency was recorded, and that was because of the airflow. So that was absolutely essential to put it into an enclosed box where we know that airflow was severely restricted. We cannot say it was absent, but it was restricted, and because of that, we are pretty sure that we measured real thing.
Okay. Yes, thank you. Thank you again for this interesting talk. Now we are turning over to Paula Garcia, and this is the talk. It's a talk with the title, The Design of Environmental Noise Labeling App for Citizen Participation. Now we are entering the smart city context. And yeah, she's coming from the GTM group, the Recherche en Technologies Media La Salle in the University Ramon Llull in Barcelona, Spain. Now it's your floor. Please start the presentation.
Hello, my name is Paula Garcia, and I will spend the article titled The Design of an Environmental Noise Labeling App for Citizen Participation in a Smart City. Well, the content covered in this presentation is a brief introduction, later on the state of art, requirements and design, the development of the application, a brief results, related work, and conclusion on future work. First of all, nowadays we are surrounded by a great variety of sounds that are recognized and discerned without paying too much attention to it. And over the last few years, there has been an increasing interest in information that they can convey, with an increasing number of studies that are done in this field. Different projects and tools have been developed and created to collect and classify labels, which is a time-consuming task as it is done manually. And the possibility of giving a basic training to citizens in order to introduce their help is a real option, because with the support of technology, they can be key actors in distributing the process among more people and volunteers. And in this present work, the main objective is to use gaming and new technologies to make classification and labeling a process that is more enjoyable for people. And an example of this can be found in schools or universities, which use digital tools for many tasks in the teaching learning process. And also gamification elements in digital and board games hooks the user to create incentives for him or her to continue playing this game. In addition, mobile phones provide permanent access to this type of games and increase the potential number of players. and this can increase the data that is collected in this type of projects. The state of art is divided into 3 aspects. The first one is gamification, that promotes the best user experience with the use of playful elements to engage, motivate, and encourage the use of the application and the game. When it comes to designing a game, and one of the most influential systems is infrastructure MDA, which is a framework which is created to bridge the gap between the game development and the game design. The mechanics describe the game components, the rules and the concepts. The dynamics describe the behavior that the game's runtime mechanics, which are on the input of the player and the outputs of others over the time. And also the aesthetics describes the emotional responses in the player where it interacts with the game caused by the dynamics. Moreover, the citizen science is a scientific research that is carried out thanks to volunteer citizens who are usually not specialists on the subject, but they actively contribute to science with their intellectual tools, efforts, and resources. And finally, the labeling sounds is the fundamental part of the project that consists on indicating where the sound starts and ends, and also how it is defined. Some examples are explained in the related work, and for example are major, minor, takachun, and set the game. Well, entering into detail in the related work, there are 3 relevant applications that have the same objective. Major minor is a web application that tags the entire audios, and the process consists in playing offline against a database so that the user tags an audio and scores according to the number of people who has previously tagged the same audio in the same way, the same time and the same level. Also, Takatune is an application that tags entire audios for a limited time. So it's a game that is played against pairs or with a bot if there is no player available online. And the user must describe the sound according to the category that is indicated during a fixed time. And once the round is over, the points are obtained according to the matches with the partner you are playing, the bot or the person. And finally, the listen game, which is an application to tag entire audios playing simultaneously against multiple players online. And the process begins with the audition of the audio, and all the players have to select if the words that describe the sound are good or bad. And they obtain feedback according to the selection done by the other players. And they add points according to the coincidences between them. So after researching this field with the related work, we have observed that they all search for techniques and mechanics to attract attention and engage users in the way that is fun, and they generate constancy to the players. Well, entering into detail in our application and following the objective defined, that was that the project focuses on the development of a citizen application to pre-level sound events in a defined recording. For the MD8 system explained before, we enter into detail to mechanics, which we used points, ranking, and levels. And the ranking, well, aims to promote the positive competitiveness, ordering users according to the points they obtain, independently from the level. And these levels can be 3, low, medium, and high. And all users start at the low level, and as the level increases, the difficulty increases, and this is based on the number of levels that are present in the recordings. And to advance to the next level, the user needs to collect points. And to collect points, the application compares the label entered by the user with those that were previously introduced in the database. We want to reward the coincidence and not innovation. So the more labels that are introduced according to the one that the user has introduced, the more points the user gets. The dynamics, the functioning of the application follows the first screen shown, sorry. And when they start at this screen where the games begin, and the user can choose to start playing or to go to the frequently asked questions, that is this screen. When they start the application for the first time, a tutorial is shown, which consists on a video and a later, for example, to start practicing. That has to be done correctly to enable the user start labeling and getting points. To the screen where the user labels is this one, where in the upper part of the screen they have to choose the label between this one shown, or if they think that any label fits with the sound, they can introduce writing a label and its description. And later in the other part of the screen, they can see the audio recording, where they have to choose the start and the end of the sound. When they have introduced all the information of that label, they have to save it and continue introducing the other sounds present in the recording. When both tasks are finished and all labels are submitted, the score obtained is shown, and later the user can see their profile screen, which shows the points and the classification. And finally, the aesthetics basically displays a message when the user changes of level, and also follows a different color pattern. Based on the functioning described before, a first prototype has been developed and tested with 10 researchers in our University of Salle. And in that test, the criteria assessed was installation, labels, navigation, tutorial, frequently asked questions, operation, design, and general aspects. The main highlights during the test were that half of the users didn't understand well the sounds, because maybe some felt that the labels shown were a little bit confusing and not always fitted with the sound that was shown. But on the other hand, most felt that the app is easy to use and also useful. And finally, the global evaluation of the app was rated as good. And from these results, we detected the need for some improvements. Some examples was the improve of the feedback received during the tutorial, so they can know why they are doing it correctly or incorrectly. Also reconsider the labels that are displayed to label the sound, and also improve the audio controller operator so that it is more easy to control the audio while it's playing. This work has presented the design of game using a mobile application to encourage citizens' participation in research and helping experts in the work of pre-labeling sounds for later analysis. And the most important aspects to consider when implementing an application of this type are gamification, citizen science, and sound tagging. which all combined generate an attractive prototype for the users to perform the task of pre-labeling in a more enjoyable way. And from this first prototype and later testing, it was detected the need for some improvements, such as improve the feedback received during the tutorial, reconsider the labels, and also improve the audio. So our future work is to make these appropriate corrections so the design and implementation are better and it improves the functioning of the app. So also continue with testing with users and finally doing a label marathon. Thanks for your attention and don't hesitate to contact us if you have any questions.
Yeah, thank you, Paula, for this very challenging and interesting topic, and of course the talk too. And other questions? So I have to look in the chat. Someone asking question, actually not. Then I starting with a short question. Do you expect bias or distortion in this kind of crowd sensing, and do you think you can address it with sensor calibration, some kind of calibration?
Well, the idea is that calibration is not needed, so that all users can label that sound, and depending on the numbers of people that has labeled that sound by a label or a word, so when they coincide, the more people that is defining that sound with that name, so we consider that that sound is described as that. Yes. So there's no need to filter or to eliminate other sounds.
Yeah. And concerning the spatial coverage of all your sensors, do you have concerns that there is a strong bias? For example, there's an area that is sampled intensively and other areas not?
Yes, maybe we have to consider that.
Yeah. Okay, any questions? Open questions? No. No, there are no further questions. So thank you again for this great presentation, and we're coming to the last presentation by Fattah, Hanafi, Sheikhha, and this is a presentation with the title Surface Reconstruction for Ground Map Generation and Autonomous Excavation.
So hello everyone, my name is Fattah Sheikhha. I'm a PhD student at Ontario Tech University. I'm proudly here to present our paper regarding the surface reconstruction for ground map generation in autonomous excavation. So, the outline, we are first going to introduce the problem, and then we go through the serious steps that are proposed in this method, from point cloud enhancement to curve approximation method, as well as the surface reconstruction to overcome the aforementioned problem, and then we review the result as well as some conclusion and the future works. So an autonomous excavator requires a perception about the surrounding environment or ground for three main reasons. The first one is the path planning, navigation path planning. The second one is to planning the digging cycle, as well as measuring or evaluating the safety indexes as well. But the LiDAR sensors are widely used in the autonomous excavator in order to scan the environment. And therefore, it's mandatory to implement the surface reconstruction algorithm to convert the point cloud data that we got from the LiDAR to a surface representation. Unfortunately, the point cloud data that we got from the LiDAR are unordered or unstructured set of data, because they miss that the information about how and which point is connected to another one. So because we have just a point cloud, and constructing the surface from a set of unordered data require high computation power and the time. So the Galvez et al. Mentioned in their paper that surface reconstruction with scattered data is challenging, and most of the methods fail to converge to the whole free and complete surface from a set of point clouds. So most of the methods assume that they have access to the additional information such as the connectivity of the points and or the normal vectors in each point, but unfortunately we cannot get this kind of data from a LiDAR sensor. So HOPE introduced a mathematical model to surface regenerated surface, which worked on any unordered point cloud. Unfortunately, they are estimating the tangent plane orientation based on the neighbor points in the space. But unfortunately, because of this estimation, the proposed methods are sensitive to noises. So as we use LiDAR sensor, we have some noises, therefore we cannot use these approaches as well. Other people or other authors try to implement some optimization approach in order to reconstruct the surface. But for example, these two authors use neural network approaches. But the optimization method requires high computation time or power, which is not suitable for a semi-real-time application such as an autonomous excavator in the construction site. So because we need to decide in a matter of seconds or milliseconds. Therefore, the aforementioned methods are prone to the error due to noises and outliers that are common in the LiDAR sensor, as well as require additional information or require high computation power and time in order to overcome this problem. And also they are not guaranteed to produce a complete and whole free surfaces. So this is the reason why we are looking to propose a method that reconstruct the surrounding ground information surface in a whole free way, which also discard the noises and the outlier and try to approximate the point cloud with a mathematical model, because working with a mathematical model is much easier rather than working with some set of point cloud data. So this is the proposed method for this project. It can be divided into three different segments. The first one is the point cloud enhancement. So we try to get the best out of the LiDAR data in order to regenerate the surface. The next approach is the curve approximation, that we try to eliminate the noises and the outlier, as well as converting the data set to the mathematical model. And then we are going to regenerate the surface regarding the approximated curves. So for the point cloud enhancement, in our study, we use Velodyne pack LiDAR, which consists 16 laser channels. These laser channels are fired sequentially, and each laser channel, each firing of laser channel may produce multiple reflections based on the environment. This specific model provides both two options, record two value. First one is the last and the strongest. The strongest is the distance from the Velodyne to the reflection that has the highest intensity, and the last one is the furthest distance reflected from the LiDAR. So in this study, we choose to work with the last option, because always the ground is the last visible object in the environment from point of view of a LiDAR. So the last model option would provide more accurate representation of the ground rather than the strongest one. Also, each LiDAR sensor reports the points in the polar coordinate. This polar coordinate data can be converted to the Cartesian coordinate using mathematical equations. However, processing the data in polar coordinate have some advantages rather than the Cartesian one. If we go with the polar coordinate, we can arrange the data points in an evenly distributed pattern or in a grid pattern. So based on elevation and azimuth, we can have the equivalent distance. While converting those data to the Cartesian coordinate, we lose these connectivity of the points together. So by having this connectivity data from each point to another one, we can ensure that we are going to generate a valid and a whole free surface at the end. The next step is to apply a curve approximation method. The LiDAR data report the data as a paired azimuth and the distance for each elevation angle. So we can, for example, this model have 16 channels so for each of which it report the pair of azimuth and the distance. The distance data may contain noise and outliers, so we need to overcome these noises and outliers. So we try to apply a curve approximation for three main reasons. The first one is retain the general shape of the signal or the distance while discarding the noise and the outlier, and having analytical equation rather than the spray points in the space. So we try to overcome both the outlier and the noises and having a mathematical equation rather than points. In this study, we used to work with the cubic Bezier curve approximation on each laser channel. So we just need to modify or adjust the position of the contour point of each Bezier curve to feed the curve to the actual raw data, and the cost function for the optimization is to minimize the deviation of the approximated curve to the actual raw data. As we can see from the laser channel 1 and 2, for example, the cubic Bezier curve did a great job to in order to maintain the general trend, the shape of the signal by removing the noises of the LiDAR sensor as well. The last part is the reconstructing the surface. So we have 16 approximated curve. We need to stitch them together to make a single surface. A linear interpolation between neighborhood curve is used to evaluate a series of points in polar coordinates. Then we are going to convert those points in the polar coordinate to the Cartesian coordinate in order to shape the actual ground of the surrounding ground. So this is the result that we got, and in the left side we have the raw point cloud that we got from the LiDAR. As we can see, it's noisy and also contain a lot of data, while generating the surface from this set of data, noisy data, require a lot of time, and therefore we need to use different methods or tune a lot of parameters to get a real valid data, a whole free surface and complete surface, while it requires a lot of time and is not usable in a semi-real-time scenario such as autonomous excavator. While in the right-hand side, we have the approximated curve or constructed surface using the method that we described. We can see that we have a more smooth and noiseless surface rather than the original one. And also we have access to analytical equation. So if you have to get more data from each portion, we can just evaluate the equation in this area and have access to the more data rather than just relying on the number of points reported by the LiDAR sensor. So in conclusion, we proposed a curve approximation-based method to reconstruct the surface of the digging ground using data set that we got from the LiDAR sensor, while we represent the surface in the Cartesian coordinate and reducing the computation time and robust to the noise of the outlier. It helps us in the allow for better identification of the ground shape to provide a solid foundation for the generation of optimal trajectory for navigation, path planning, digging cycle generation, also accurate tracking contour, as well as safety evaluation. However, our work has some limitation. For example, we are using a linear approximation between neighbor laser channel, and also as we use the cubic Bezier curve, it shows a poor performance on detecting the sharp edges. So if the ground surrounding ground have some sharp edges or high oscillation, and this method cannot provide such a good performance. So in the future, we may work on the other advanced method to interpolate between neighbor laser channel or and also improve the sharp edge detection, and may also add some boundary constraint to the equation. For example, we can maintain the slope or curvature continuity at the boundaries of the regenerated surface. So thank you for your time. And if you have any questions, please let me know. I would be more than happy to answer the questions.
Yeah, thank you, Fattah, for this interesting talk. And I look in the chat for question. I have a question. With which methods you will deploy or to apply to improve the detection of sharp edges?
Actually, we are working on a process. For example, we are using one single cubic Bezier in order to approximate the curves. One way is to increase the order of the Bezier curve, so we can use a higher one, but it's also prone to the oscillation as well, and also it requires more and more time, because we need to optimize the contour point of the cubic Bezier. So solving the problem this way may increase the computation time as well of the other approaches. The current approach that we are using is to use a piecewise cubic Bezier, so we can try to fit different sub elements of the cubic Bezier to the curve, and if the cost function is higher than the threshold, we can bisect the element into two sections and try to use that. So in general, we can use the divide and conquer approach in this method.
Yeah. And what's the impact of noise, sensor noise? Do you have investigated it in a deeper, on a deeper level?
Yeah, actually, the sensor that we got is has about plus minus 3 centimeter error range. So the approach that we used, we tried with the ground truth data, and the result would be around 7 centimeters. So in comparison with the 6 centimeter error from the LiDAR, we reached the accuracy of the 7 centimeter by maintaining noises. However, in the construction site and digging cycle, the order of the accuracy in the range of plus minus 10 centimeters, because they are not that much exact precise, because they are the construction sites. So the error that we have right now is sufficient for the construction equipment.
Okay, thank you for the answer. And
thank you.
I look in this chat, there is no further question I see. And in the question answer box, there's no question anymore. Okay, thank you, Fattah, again for your talk. And now we are at the end of our session. We have short time for any further questions and discussion. So if you have questions, you can ask them now. If this is not the case, yes, I will thank you again, all presenters, and of course, all the listeners here in the audience, and maybe Anna have some closing words, and then we are at the end of the session. Thank you.
Yes, thank you, Stefan, again for chairing this session. I would also like to thank all the speakers for their time and their contributions to these live sessions. Again, also to our attendees, I hope you found this live session interesting. Just a final reminder that the recording of the live session will be made available as soon as possible on the conference webpage. And also, as I shared through the chat, feel free to join us on November 8th for the second live session of the conference. I wish everyone a nice day, morning, evening, wherever you are in the world, and that would be for the first session of this conference. Bye-bye.